Yeah, let me start with explaining what federated learning is. Thank you. So in federated learning, we just heard a federated learning paper. For you not to get confused, the previous authors were trying to use federated learning to predict energy, like load or production. We're trying to schedule the federated learning training itself. So this is carbon-aware computing in this sense. In federated learning, we try to train a common model across different data silos. So other than in traditional machine learning, where we have all the data in one central location, in federated learning, it's distributed across different, what we call clients. These clients, for some reason, want to train a common model, but they do not want to share their data, or they cannot share their data. A common example is hospitals that want to maybe train a common model for skin cancer prediction, and they want to use as much data as possible, but this data is very privacy sensitive. Or in the previous example, we've seen this could also be households. So what we're doing now in federated learning, we're distributing our global model, locally train at the clients, and then send back the updates to somehow average them. And then we start a new training round. Again, select a subset of clients, distribute the model, train locally, and send back the updates. Now, the interesting part is that we usually only train on a subset of clients. We do not use all clients. This has to do with efficiency. Otherwise, we would be updating across a large variety of different gradient signals, and we just converge a lot faster. Slower. So we only select a subset, and this makes this a very interesting use case for carbon-aware approaches. Because on the one hand, we have this location scale. So we're doing a globally or like a distributed training could be distributed across many regions. But also we have iterative training over time. So we can decide when and where to compute. And now the motivation, we actually just heard a talk about curtailment, is that we're seeing an increase in curtailments around the world. California in 2022 curtailed around 7% of their solar production. In Germany, we have a similar problem with wind, that we're producing all the wind in the north, and our grid is not strong enough to get it to the south. So we're having more and more curtailment, and at the same time, also in computing, we're having a lot of spare resources. In cloud computing, data centers are usually highly over-provisioned to allow for scalability, and also on-premise hardware is often underutilized. So what we are asking in FedZero is, can we somehow match the two, and can we perform a federated learning training using only excess resources? And how can we do that? And now this comes with a few challenges, of course. The first challenge is, okay, we have very variable resource constraints. Clients appear and disappear in weird patterns. How can we perform a reliable training under such constraints? Second, clients might share the same power source. So they might compete at the power at runtime for the power at runtime. So we need to account for that in client selection and of course also during training. I will talk about that more in a second. The third point is one of the hardest. We need to assure fairness. So some of these clients might have access to a lot more excess energy, a lot more spare computing capacity than others, but we do not want the final model to be biased just by how much sun there is in a certain region, for example. And lastly, we want an approach that is robust to forecasting errors and also scalable. So in cross-silo federated learning, we usually do not have that many clients. It's just a couple, but the approach could as well be useful for example, training federated learning on an autonomous vehicle fleet, where we can easily have tens of thousands of clients. And it all boils down to a big trade-off, which is between model performance, the convergence speed, and carbon efficiency. So you cannot optimize all three at the same time, unfortunately. And as we do not want to sacrifice on model performance, we sacrifice on convergence speed. So at times we might slow down the training, pause the training to wait for certain clients to become available. So we still get a good and fair model while being very carbon efficient in this approach. Now, again, back to these power domains and the common power budget. I just wanted to explain this one more time. In cross-silo federated learning, we can have multiple clients located at the same physical infrastructure. So they may run in their virtualized, encapsulated environment, and they do not want to share data, but they still might run on the same infrastructure that is maybe powered by some on-site or off-site power source directly, or as well could be just powered by, or could be executed over maybe future time-based renewable energy certificates, which could also span across multiple data centers. So maybe they have a certain budget of renewable energy that they bought for a certain time and certain location, and we have multiple clients that compete for this energy. So during client selection, we maybe want to take care that we spread out the client selection across different power domains, because otherwise they might slow each other down. So to quickly give an overview over the protocol, at the beginning of each training, clients have to register with the server. This means they provide their computing power. So how much can they compute? The energy efficiency can also be under different conditions, and the power domain that they belong to. Then at the start of each training round, FedZero collects forecasts for excess energy, as well as spare capacity on the clients. And based on these forecasts, we perform client selection. I will get into detail on this in a second. And then we train locally. And here it is really important that clients constantly stay in contact and communicate their progress to some control plane, because of course, real life conditions and runtime conditions can be quite a bit different from what we originally forecasted. So we maybe need to re-attribute energy at runtime to avoid stragglers, to avoid individual clients that fall behind schedule and thereby slow down the entire training. We want to avoid that. And then in the end, as usual, we aggregate the updates, somehow get a new global model, and start the next training round by querying a fresh set of forecasts. So the only thing I want to get a bit more into detail is this participant selection, because this is like a core component of FedZero, and FedZero iteratively searches for each round for the smallest possible round duration for which the following optimization problem solves. And we do this through an iterative search, so like a binary search on D. And we factored out D of this optimization problem because this way we were able to show that this entire thing scales linearly with the amount of clients and n log n with the round duration, the forecast resolution in which we search. So this is a scalable approach. The optimization problem itself is quite simple. We select n clients who maximize the statistical and system utility of the training round under the forecasted resource constraints. And optimizing for statistical and system utility is quite common in federated learning. So system utility means how much are we computing? This is actually something we're optimizing directly. So we're optimizing the amount of mini batches that are computed at the individual clients within certain bounds. And the statistical utility is something that you can come up with. We by default are using the approximation for statistical utility as defined in ORT, but you can come up with another function. It depends on the use case. So in some use cases, you want to have clients represented by the amount of data that they have. In some cases, you have something that's called group parity, where you just want different groups of clients to be represented in the model equally. So there's different fairness metrics that you want to optimize on, and FedZero works with all of them. What we did now by default is once a client participated in a training round, we exclude it from future rounds. So we set the statistical utility to 0. And we re-include it in the training with a certain probability, which is inversely proportional to its previous participation. And we will see in the evaluation that this is actually a very simple way to avoid that certain clients that have access to a lot of resources dominate the training in an unfair manner. All right, so for the evaluation, we used real load traces provided by Solcast. It's like a solar data provider. So it's really real solar load data and also solar forecasts. For the systems, we use the Alibaba GPU cluster traces. And we perform actual federated learning trainings, of course, but we model the system behavior through discrete event simulation. This allowed us to progress. For example, here we see in the upper left in the scenario, all the clients are co-located, the excess energy patterns correlate a lot. And at night, we never have excess energy because we're only considering solar here. So this discrete event simulation allowed us to fast forward for 8 hours during training because we run trainings over quite a long period. It's 1 week. And we performed a bunch of experiments on these 2 different scenarios. In the second scenario, clients are distributed all across the world. So the excess patterns correlate a lot less. We had 7 baselines and a variety of different model dataset combinations, lots of different modalities. So the first 2 are image classification on convolutional neural networks. Then we have next character prediction, so text on an LSTM. And the last one is keyword recognition, so speech on a small transformer network. And I do not really want to get into too much details on the results because you can have a look at the paper. But we showed that we were able, across all experiments, to converge significantly faster than any baselines, like around 30% faster. That means 1 or 2 days earlier, our model reached some target accuracy. We also used a third less energy to perform this training. And across almost all experiments, we managed to improve the final accuracy by a couple of percent. In some experiments, we matched the best performing baselines. There's only one set of experiments where I want to put a bit more focus on, and this is this one. This is the fairness. So what we see here is the average participations of clients from different energy domains. So this is the globally distributed scenario. We have 10 different cities globally distributed. And in our experiments, we select always 10% of all the clients. So we would expect that on average, 10% is the average participation of each client as well. And we can already see here that, for example, in Cape Town and Sao Paulo, there is obviously a bit less energy available than in the other regions in the data set that we have. So here FedZero is already okay. It's already a bit fairer. The standard deviation is a bit lower. But this gets a lot more interesting in this analysis where we gave one of the power domains infinite energy. And also all the clients in this power domain have no background load. So they can use all their compute capacity only for federated learning. And here we can see that in the random client selection on top, this region is heavily over-selected. So in the end, it will dominate the model. Other regions and the data from other regions will be underrepresented in the model because Berlin is a lot more available than the other regions. And in the second approach, ORT, which is like a state-of-the-art client selection approach in the systems world, it's even worse because ORT focuses and targets clients with a high system utility. And these clients have a very high system utility because they have no background load. So here it's getting even more unfair. And we can see that FedZero doesn't do this. FedZero only slightly leverages the additional resources, but doesn't introduce an unfair advantage. And this really shows in the results. So we also here managed to improve, in this example, managed to improve the accuracy by 1.5%, converge a day faster, and use a lot less energy than the baselines. All right, with this I come to an end. This is actually only one out of two other authors here of the other federated learning paper, actually. Not yet, no, because tomorrow is a paper with a very similar goal. Found it very funny. Luckily, we have two different objectives here. You. Yeah. Sweet. Okay. Yeah, luckily, like I think you are like optimizing for federated learning training within a carbon budget, right? This is a very different objective, of course. So, but it's the same idea. So we introduced FedZero here. All the data sets and all the code that we used is publicly available. And what we will investigate more in the future, I think what is the real killer questions that none of the two papers really answer yet is what is the trade-off? Like, what is the trade-off between training performance, convergence speed, and carbon efficiency? Because of course, zero carbon is just a thought experiment. In practice, you need excess energy available at all the clients. You do not always have that. So really want to know, okay, 20% slower, how much carbon can I save? 30% slower, how much carbon can I save? I think this is like really a very interesting question. Okay, and with this, I'm already coming to an end. Thank you.
So I have a question about the time to accuracy results that you have shown. So my understanding is because you are implementing FedZero, you are not doing random client selection, right?
Yeah, exactly.
So it's not intuitive to me. Why would you have any better results than a random one? Because you are not going for any improvement in time to accuracy, but rather going for improvement in carbon reduction, right?
Sorry, yeah, I should have made this clear. So this is, unfortunately, I do not have a plot here on this. This is random client selection under the same resource constraints. So random client selection, which is also only allowed to train on excess energy and spare capacity. So we also compared, of course, to a completely unconstrained environment, and would say in 50% of the experiments after 7 days, we matched the accuracy of the unconstrained one, and other experiments not. But here, all the baselines, there's 7 of them, were also operating under the same constraints as FedZero, and only within these constraints, we are faster and more energy efficient.
So I have yes, thanks for the clarification. I have a different question. So it seems like if you're only selecting 10% of the clients at any round, so 90% of them are sitting idle, right?
Yeah.
So given that the money that they spend to get the resources to run these models, did you put any justification, or do you have any justification for actually doing that?
For only selecting a subset?
No, I'm talking about, let's say I am one of the clients. Why would I keep my system 90% of the time sitting idle?
This is just one compute workload. This is basically being distributed on top of excess resources, right? So we still want to use as little compute as possible to train our model. And the reason why we're only performing federated learning usually on a subset is a bit the same argument than why we're doing stochastic gradient descent over gradient descent. It's just converging faster with less compute.
Actually, that's not my question. My question is, if you have the infrastructure and you are only using 10% of the time, then 90% of your infrastructure is sitting idle, right?
I mean, in most of these scenarios, 90% of these infrastructure don't have excess energy patterns at this time.
No, but you know, the compute system, right? The servers that are running the system, right?
Yeah.
They are not doing anything. Or if they're doing something, then it's no longer zero carbon, right?
I'm not sure if I get the point, because like from these 90% that are not being selected, most of them don't have access resources available at the time. They cannot compute.
But how come they have access resource? How they get the servers other times? So you're talking about access resource in terms of power only, right?
Mm-hmm.
You're not talking about server capacity.
Both.
So they do
Both.
have. Well, how the server capacity change all the time? It should be fixed for a long period.
Depends on the use case, I would say. So what we used is these Alibaba GPU cluster traces, and we just selected randomly 100.
But they have like a fixed number of GPUs, right?
Yeah, but they're not always all utilized.
Right, that's what I'm talking about. Like, they have to pay for the GPUs, right? So if it's sitting idle, they have the embodied carbon and other things, right? So my point is, it's actually not good to leave things idle. Even though we are always trying to move things around here and there, leaving something idle is also not good.
No, absolutely. Yeah. But this is, but I mean, this is one idea how to fill these gaps, right? I mean, if you're doing cloud computing, you're always searching for flexible workloads to fill these gaps because you do not want idle infrastructure. Yeah, it costs money. It's useless. Yeah.